Okay, now let us look at these are the short term properties, very important properties we have focused, which is the concrete stress strain curve responses. Now let us see the significance of long term properties. Now as we can see, the concrete can undergo deformation over time due to three different mechanisms, which are the three common mechanisms. One is the creep, another one is shrinkage, another one is temperature. Now let us look at, if I start plotting the variation of strain in the y axis and with respect to time in the x axis, let us see what is happening. Let us say that I start casting at this point of time, right. Then let us see what is happening. So you see here, you start mixing, and then you tend to have, let's not forget about the material can undergo due to because of the hydration process and all. I think let's say that this is your casting time, and then we say this is the time where I am actually stopping curing. Okay, so this is the start of drying. That means I have stopped curing concrete. Okay, this is the time that I have, let's say I have casted cubes, it is undergoing some expansion spelling, and then I have taken out from the water, and this is the time that you stop curing. So the moment you stop curing, right, what happens, due to the chemical reaction and so on, there is something called autogenous shrinkage that happens. This is the shrinkage happens to the concrete, right, and then you have drying shrinkage. So autogenous shrinkage is the reduction in volume because of the chemical reaction of different constituents that you start putting, right. And then you have drying shrinkage, because the drying shrinkage again it will, because that is the reason this is the time from the mixing it starts coming, right. This blue color curve, the darker color, it goes like this, right. Autogenous shrinkage starts even at the moment you start mixing water, the hydraulic reaction starts, and then this is the way it is happening. But then we are interested in what is the volumetric change that is happening after we stop curing, right, because while you curing there is no external escape of the water, right. So your drying shrinkage will start at that point of time, and then the concrete will undergo more hydration process. In that process again it will start losing the water. So then this is your autogenous shrinkage due to chemical reaction, and this is your drying shrinkage that is happening from escape of the water to the outside environment, right. Now this is the shrinkage strain. So this is shrinkage is contraction. So these are the two shrinkages that happen, autogenous shrinkage and drying shrinkage, and typically the drying shrinkage is much higher than the autogenous shrinkage for low strength concrete. I can say when the moment you go for high strength concrete, depending upon the amount of cementitious material that you use, autogenous shrinkage can also be comparable, but typically they are lower than that of drying shrinkage. Now this is the total shrinkage. So when I add these two, this becomes your total shrinkage, right. Now I start applying the load. So this is the T at which I apply the load, applying load. Okay, so applying the load. So I apply the load. Then what happens? There is an initial strain. So this is the total strain from shrinkage, and this is the from here to here I have load induced strain. Because of the application of the load, now there is a strain. Now at this point of time I have stopped applying the load remains constant, but having said that, the load is remaining constant, that means the stress is remaining constant, but the concrete will still undergo strain. That is what we call that as creep. Again creep, we have two things, basic creep and drying creep, but basic creep is when you prevent the escape of the water, then you quantify the creep, that's we call that as a basic creep. And but typically for practical system, you don't cover it for preventing the loss of moisture. So the creep is both of them together, you call them as a creep strain, which has two components. One is the basic creep, another one is the drying creep. So you can see here at this point of time the initial strain is applied, but then you tend to, though the load is remaining constant at this point of time from here, but the creep, it is evolving like this. Okay. So, this is your total creep strain. So, you can see here, if you have to calculate what are the different types of strains that you have this from shrinkage, this is purely from load, and this is from creep. So, you can see here creep strains can be much higher than that of load induced strain as well. So, that is a thing that we have to keep in mind, especially in pre-stress, because you put lot of stress in concrete, the creep can be quite significant. So, that is what we say, this is the stress induced strain. So, that means whatever that is because of the load plus load remains constant, and then the creep strain is evolving. So, that initial strain due to load plus what are the creep strain, when we add them up, that is the total strain induced by the stress. So, but then this is basically the drying shrinkage strain. So, but if you add the stress induced strain and shrinkage strain, then you get your total strain. So, you can see here that strain has different components. So, it is not only from the load, you also have strain that is coming from shrinkage, and we also have strain that is coming from creep. So, that is the reason epsilon total can be from epsilon load plus epsilon shrinkage plus epsilon creep, right. So, we have to make sure that we choose proper material mix design and proper curing, so that this can be reduced as much as possible, that is shrinkage and creep, we want to reduce it as much as possible, right. So, that your overall net strain is within your acceptable limit. Now, this is with respect to concrete undergoing various strains, which is creep strain. Now, let us look at what happens to pre-stressing strand. Okay. And as we can see here, the strand we have discussed in the previous part, that we have pre-tensioning and post-tensioning, and they behave actually like a rubber band. You stretch the steel, you stretch them to the strain level you want. Strain multiplied by elastic modulus will give you basically the stress. So, typically the jacking stress is 75% of your FPK. So, that is the level at which you stress them. Then immediately you will have some anchorage and seating loss, because the wedges have to go inside the anchor and it has to sit, right. So, there will be some seating loss, and then the anchor plates also can undergo some small deformation. So, that is a small loss that will happen. Then what will happen? The stress will further reduce, you can see here, because of the relaxation and temperature. Now, what is relaxation? So, at constant strain, the stress will keep reducing. So, now as I said, steel is going to be like a rubber band. So, you stretch it, the deformation remains constant, but however the force or stress required to keep it at constant strain will keep coming down. So, that is the relaxation. Creep, under constant stress, the strain is going to keep increasing, but in relaxation, you keep the strain as constant, but the stress that is required to keep it at constant strain will keep coming down. So, that is this is nothing but the relaxation and temperature loss. In addition to that, while you do the transfer of pre-stress, that means when you do the transfer of the pre-stress, the concrete will undergo some shortening. So, because especially in case of a post-tension system, you are reacting against the concrete when you put the wedge and then you lock them, right. So, that time you have again further losses, right. That is your elastic shortening. So, that is this your elastic shortening, right, this value, right. Now, because this all the stages, strand tensioning, pre-stress transfer, for example, let us say you have a precast element, on top of that you are putting a bridge deck. All these activities, they do not happen at one time, they happen over a period of time. Okay. So, for example, from here to here I can have about 10 days. From pre-stress transfer to deck placement I can have more than 2 months also, right. It is possible, right. And then Once all the decks are placed in the bridge, then you allow your other superimposed load. So, this can be another 1 month. Then by the time you open the traffic for live load, this could be another 2 months, right. So, this happens over a long period of time, okay. So, that is the reason the losses also keep happening. Now, the moment you see here, this is very interesting. So, this is the loss that is happening, okay, to the pre-stress. Now, there is a small increment in stress that is going to happen. Why? Because when the loads are acting, that is going to produce more tension and the stress in the strand will go up. Then again further losses will happen. Then the moment you have more superimposed load, again there will be some increment in your stress. Then further losses will happen, right. So, this is the point at which you see here there is some increment in stress due to live load. So, overall if you see here this, because this initial stress FPI we call that, is so high and the losses are keep happening, and there will be an increment because of the load that it is coming, but the increments of stress due to the loads are not that high compared to the initial stress, because the initial stress itself is so much and losses are happening, but because of the deck placement, superimposed dead load and live load, there will be an increment in stress, but that stress is not going to be comparable to that of the loss that what I am going to have. So, that is the reason you see here from here to here, it's 0.75, this could be probably at this level, you can be probably around FP at this level. If you see, it may be about 0.7 FPK. So, the difference is not really very significant, 0.75 to 0.7 or maybe 0.65. So, what I am trying to tell here is the change in stress under service loads because of the external loads is not very significant. It is very close to that of initial stress only, but there will be losses that will be happening over a period of time that we need to account for them in our design for accurate estimation of your behavior. Okay, now this is what we have said. Creep is defined as the long-term deformation caused by application of loads for long periods of time. Usually it happens for years, right? And creep strain occurs due to sustaining the same load with time. So, that the definition is under constant load, constant stress, the strain keeps on increasing. So, that is the reason we say the deformation is typically divided into two parts. Okay. The first one is called elastic deformation, right, occurring right after the applications of the loads because of the load induced effect. The second one is because of the creep, right. So, when we do the section analysis, we have seen, when we do the section analysis, let us say you have some reinforcement here, right. Now, due to loads, typically you get this kind of a strain distribution, okay. So, and this is what we call that as curvature, okay. Now, over a period of time, this is due to load, right. Now, if the load is remaining constant, but again what will happen is the compression side will undergo more strain. If compression strain is undergoing more strain, means what will happen? This fellow will try to push it like this. So, this curvature, let us say this is P1 and this P2 is going to be more than P1, because the strain at the top is going to increase more. So, to satisfy the equilibrium, again there will be more tension in the bottom also. So, that is how we get this long term deformation. Okay, long term deformation, right. Now, this is the definition of your variation of your creep strain with respect to time. If I plot again the strain in the concrete on the y axis and with respect to time in the x axis, let us say that this is the initial load induced strain, okay, this strain, and I am keeping the load at this point of time. That means strain also ideally should remain constant, but it will not remain constant. The strain will keep on increasing like this, okay, that is what we try to plot here, okay, that is what we try to plot here, right. And when it is, this is loaded constantly. So, this is your instantaneous strain or deformation, right, and then this happens. So, you can see the slope here is higher compared to that this slope, right? This slope is less. So, you see here the creep is happening faster at the initial time and then it slows down over a period of time, right? Now, when I remove the load, what will happen is this strain, whatever that epsilon instantaneous that I have applied, that will be recovered, that is called that elastic recovery. And then some portions of the creep strain also I will recover, but I am not going to recover all the creep strain. So, this is the total creep strain, right? But if you see here, the entire thing we are not recovering, only we are recovering a part of it. So, that will leave with a permanent or a residual deformation in the system that we need to account for that in our design. So, that is a major problem with creep, is the long term deformations will be quite significant. In fact, the long term deformation can be as high as 2 to 3 times that of short term deformations. So, when you check for deflection, especially for pre-stressed members, and they are going to be predominantly in compression, you will have more creep induced deformation that we need to account for them in our design. Now, what are the factors that affect creep? And we can see that it is basically happening from the water that is there in the gel pore, capillary pore, and between the interfaces of your calcium silicate hydrates in the concrete, that will try to come out of the system. So, there will be some deformation in the concrete. So, somehow the major culprit for creep is because of the unutilized water in the hydration process. So, we have to cure the concrete really well. If you are able to cure the concrete really well, the creep will be less. And also steam curing helps to reduce the creep. Typically for high performance concrete systems or ultra high performance concrete system, steam curing is usually adopted. Now, high strength concrete, again we develop high strength concrete itself first by reducing the water cement ratio. So, typically they will have low water to cement ratio, but then workability is arrived at by adjusting the dosages of superplasticizers. So, they tend to have smaller creep than normal strength concrete. Now, again creep also increases with temperature. So, we need to make sure that at the early ages, typically concrete is not exposed to high temperature, probably you have to cover it up so that it is not going to be exposed to high temperature. Now, again higher the humidity, less will be the pore water which can escape. So, that is if you are in a very humid region, then you know the moisture content in the air, it is already high. So, it cannot absorb more moisture from the outside, right. So, higher the humidity, less will be the pore water which can escape from the concrete, that will less creep. Now, again concrete with high content of cement paste also will tend to creep more, that also we have to keep it in mind. Now, again by adding more reinforcement on the compression side, it will not let the concrete to undergo more strain. So, in that way it will greatly help in reducing the shrinkage as well as creep. So, putting compression steel not only from strength point of view, from long term point of view, long term deflection, to tackle the long term deflection and shrinkage also is a good idea. You can put some nominal reinforcement on the compression region, that will greatly help in reducing your creep strains. Now, this is another important thing. Now, when you have a less surface area, or we can say large volume to surface area, when you have, they have less creep. Or in other words, if you have a large surface area to volume, more the surface area for a particular volume, if surface area tends to increase, then more is the exposed surface through which the water can escape. So, typically large members will have large volume to surface area, that means less surface area, they tend to have less creep. So, this is what we try to note by this factor called H0 in the future slides. It is typically indicates the volume to surface area. Higher the H0, you will find that less will be the creep deformations that we will discuss in the coming slides. Okay, now how do we address this creep? Okay, creep is inducing long term deformation, which we need to be aware of it, right. And typically we try to account for the effect of creep through this creep coefficient. Okay, what is the definition of creep coefficient? So, IS code recommends using this creep coefficient as this ultimate creep coefficient. Typically what we try to do is, because of the creep, I said stress remains constant. For example, if you look at the stress strain curve, Fc epsilon c. Now stress remains constant, okay, originally at this point. Now what we are saying is, at constant strain, strain is increasing. If the strain has gone up like this, now what happens? My elastic modulus is nothing but stress divided by strain, right? If the strain is increasing, then what will happen? Elastic modulus will reduce. So that's what the code is saying, that you can use creep coefficient to account for that increase in strain, or in other words, which can lead to the reduction in elastic modulus by this factor. So you take the initial modulus and then divide it by 1 plus phi, and phi is typically greater than 1. So you get reduced elastic modulus, or is also called as effective modulus of elasticity. Okay. So the creep coefficient is used to account for the increase in strain in an indirect way by reducing the elastic modulus. So if I use reduced elastic modulus or effective modulus, then my deflection estimations are going to be higher. Okay. Now you can see here, this also is a function of when I start loading the concrete, right. So for example, if I start loading at a young age of concrete, you know that concrete takes sufficient amount of time for complete curing, right. And at 7 days, it might of a normal thin concrete, if you take it, only 70% of the hydration, it would have happened. So that means a lot of unutilized water is still in the systems. At that age itself, if you start loading the concrete, your creep effect will be high. So that is the reason the creep coefficient is high when you start loading the concrete at a younger age. But if you allow the concrete to cure for a longer period of time and start loading at a later stage, then the creep coefficients will come down. Now, lower the creep coefficient, that reduction in your elastic modulus will also be lower, right, because this phi is in the denominator. If I take smaller value, that means my effective modulus will be higher. Okay. So that is what the code is saying, right. So now this is the definition, as we can see somehow, but we know that the strain is increasing. Now this phi is indirectly captures variation in strain. That's what we saw this. If I take at this point, this is the strain, right, epsilon. If I take at this point, this is my strain. So somehow I have to account epsilon 1, epsilon 2. Account for this variation in strain depending upon what time that I am dealing with, right. So the phi should be function of time t, and there is also something called T0. T0 is the initial age at which that I am going to stop curing. Okay. So T0 is the time up to which that I have cured the concrete, right, because longer the curing, less will be the creep. So that also somehow I have to take into account. Now you can see here, stress by strain will give me elastic modulus, or in other words, strain will be given by FCI, stress divided by the effective modulus. So somehow we have to account for this. Now what are the factors this creep coefficient should account for? Now this is the coefficient. So ECE, as you know, we can calculate ECE. How do we calculate ECE? ECE is, we have seen it in the previous slide, which is EC divided by 1 plus phi. Now if I calculate phi, then I can calculate ECE, right. So to calculate the effective modulus, now I need to know the variation of your creep coefficient. Now this creep coefficient, as we have discussed in the previous slides, it takes into account the volume to surface area of the member that you are considering for calculation, and by through a factor called Kc, and there is another factor called Kf, which accounts for the influence of concrete strength. We have seen that higher the strength of the concrete, lesser will be the creep, because we are fundamentally assuming that we are going to use low water to cement ratio. Then again, higher the humidity, lesser will be the creep, right. Again, higher the T0, the time of curing, again lesser will be the creep. So all these factors have been calibrated into this equation, and that has been verified with a lot of experimental data, and this equation has been proposed to vary to indicate the variation of a creep coefficient over a period of time. Now, you can see this is strength of the concrete. Higher the strength of the concrete, Kf will be less again. Similarly, Kc is a factor that accounts for volume to surface area. Now, as you can see, surface area is coming in the denominator, right. So, if you have larger volume to surface area, you will tend to have lesser creep. Okay, all these factors have to be somehow built into all this equation. So, let us see now how do we do that. There is one more factor that we need to account, because creep is happening over a long period of time. Okay, so now let us say we design a 20-story building like this, and then we are trying to calculate in the ground floor column what is the effect of creep. Now, see, for example, this column is not loaded all of a sudden. Construction of each floor takes some time. So, the loading happens in a gradual manner. So, the loading happens in a gradual manner, and I do not apply the loads all of a sudden. So, the stress is applied is varying gradually with respect to time on this column. The strain at T days after casting, when the initial stress FCI applied T days after the casting is given by this equation. Now, you can see what is the advantage. We know the strain is final strain is given by FCI by EC only, but we are saying that this is the initial stress, but in addition to that there is also extra stress that are happening, that is not happening suddenly, but it is happening over a period of time. So, when I start loading the element gradually, again the creep effect has to be lesser. If I am applying all the load sudden, then the effect will be more pronounced, but if I am applying the load gradually, the effect has to be, creep effect has to be less pronounced. So, somehow we have to account for this in the variations of your concrete strain. So, that is what people have said. Okay. Now, to account for that, we are saying that, for example, if you take this red color column where it is being loaded very slowly, then I cannot actually use this EC adjusted model. I have to reduce by some factor called reduction factor or an adjustment factor. Okay. So, this is how we calculate your EC adjust, not just by ECI by 1 plus phi into T naught, that phi has to be reduced, so that it accounts for the gradual loading of the column. Right. So, that factor is called a relaxation coefficient that was developed by Trost by his experiments, and then it accounts for reduction in the creep, because not all the stress is applied at the initial time Ti. Okay. Now, let us look at how the codes actually calculate the creep. Okay. Anyway, so in addition to factors like shrinkage also influences creep. Creep again depends upon how much stress that you are putting in the concrete. Higher the stress, higher will be the creep. Now, age at loading. If you are able to delay the age at which you start loading the member, then the creep will be less. But if you start loading at a younger age, creep will be more. And duration of loading, that is what we said. Depending upon how much time that you have loaded the member, the creep is going to vary, right. So, if I am taking, let us say 10 years after the construction, the creep will be higher. But if I am talking only at 28 days after construction, again it will be lesser. So, creep is again, it is typically proportional to the stress if the applied stress is not more than 1/3 of the peak compressive strength or the characteristic compressive strength. So, if you are still in the elastic regime of the material, then we can say that creep is directly proportional to the amount of stress that it is on the system. Now, this is how we calculate your creep coefficient. We have said this is the total strain and this is your initial strain. This is the definition of your creep coefficient. Now, for epsilon Cc of T is creep strain at any time T which is greater than T naught, and epsilon Ci at T naught is the initial strain at the time of loading, T naught, right, and T naught is the initial time of loading, right, when you start loading or how much time you have queued and then you start the loading, right. Now, let us look at now what is this. Now, how do we calculate this phi factor? Okay. Calculation of phi factor, and this is the at any point of time T. Okay, let us say I can do the calculation at 1 year or 2 year, that is the T that we are talking about, and T naught is the the age of loading. Maybe you start loading at 28 days or 56 days. So, it is given by two factors, which is phi naught and beta t comma t naught. Phi naught is the notional creep coefficient. So, this is what we say. This is the variation of a phi naught. So, phi naught, you see here, this is the final value that is assumed to arrive at 70 years. That is a notional creep coefficient, the maximum value that is possible for a particular material system. Okay. Now, depending upon at what stage that I am calculating, I need to reduce. This is nothing but some kind of a reduction factor. Okay. So, this is the maximum value that is possible, or a notional value, which happens at 70 years, that it is shown in this graph. Okay. Now, you see here, this is asymptotically, where the creep coefficient reaches asymptotically with time at 70 years, and then beta t comma t naught is the coefficient describing the development of creep with respect to time. So, it is something like a reduction factor. I take the maximum value, and depending upon what time since the loading that I am doing the calculations, I reduce it by that particular magnitude. Now, how to calculate that notional coefficient is, again, there are some three factors. The factor that accounts for humidity, right. So, that factor that accounts for humidity, and then you have factor that accounts for concrete strength, and then the time of loading. Okay. So, these are the three factors. Now, let us look at each one of the factors. Phi RH is the factor that allows for the effective relative humidity on the notional creep coefficient. As you can see here, there are two equations that have been given, one for concrete strength less than 45 megapascal, another one for concrete strength more than 45 megapascal. So, what you can see here, this is the H naught, which is the volume to surface area coefficient. Okay. This is the coefficient that describes volume to surface area, right. And higher the relative humidity, we know that less will be the creep. If it is a dry region, more possibility of escape of water, so more will be the creep. So, if it is relative humidity is high, that means it cannot absorb the moisture, so less will be the creep. So, these different coefficients have been given. Similarly, H naught we have seen, higher the value of H naught, less will be the creep, right. So, because that will have lesser surface area. Okay. Now, this is how we define H naught, which is nothing but 2 into cross sectional area by perimeter. If I take a prism, I cut the area, the cross section area is AC, and perimeter is basically on all the four sides which are exposed for. Let us say if I take a column, perimeter is your basically the exposed surface. That is why the H naught is a factor that accounts for. If I take unit length, area into unit length will give me volume, perimeter into unit length will give me the exposed area. So, that is the reason this H naught is a factor that accounts for volume to surface area, right. Now, AC is a cross section area, U is a perimeter that we talked about, beta FCM is a factor that allows for effect of concrete strength on the notional creep coefficient, which is given by this beta factor. Now, again, higher the strength of the concrete, less will be the creep. So, that is somehow we have to account for that. And beta T naught is the factor to allow for effect of concrete age at loading. So, that means, as we have seen, if I am loading the concrete at later ages, creep will be less. At younger age, because it is not cooled well, it is very vulnerable, and it has a lot of unutilized water that can escape out of the system. So, beta T naught should also account for when you start loading the concrete. So, these all those things are taken into account. Again, this is what it is, right. So, this way we calculate your values. The code also gives you directly, instead of this equation, I can directly get my notional creep coefficient using this table, which is given in IS 1343. Basically, this table gives you directly the value of phi naught that happens at 70 years, which is a notional creep coefficient. Now, you can see here, if as I told you, this is the volume to surface area, right. So, if this volume is higher, then the creep will be less, right. So, that is what you are saying. So, this H naught. If the age of, let us look at only the age. At let us compare the age at 1 and 90. For example, 90 days for H naught of 50 mm has only 2.5, but age of loading, if it is 1, it is 5.8. You can see here, when you start loading at young age, creep is more. Now, let us look at for the particular age, let us say 28, and let us look at now what is the effect of H naught. What is the effect of H naught? You can see here that H naught is nothing but volume to surface area, right. If volume to surface area is increasing, that means when H naught is increasing, what is happening to creep coefficient? It is to less, because now I have more volume to surface area, that means less surface area for escaping of the water. So, the creep coefficient has to be lesser. So, that is what it is capturing. Higher the H naught value, lesser will be your creep coefficient. So, that again these values have been given for, one is for dry weather condition, another one is for a humid condition. You can interpolate depending upon the relative humidity that you have. So, this table directly gives you phi naught, that is what we have, and this is what we have seen, and you can see here higher the volume to surface area, less will be the creep, it is only 2. Now, if more surface area, creep is 3. So, this is for T naught 28 days and FCK 30 megapascal. So, you can see that more the surface area, or in other words lower the H naught value, higher will be the creep, right. So, we can say that when the end results are not very sensitive, the final creep coefficient value can be taken from the previous table for normal built concrete between M30 and 60. Now, these table, the notional creep coefficient that what we calculated, they were derived based on certain assumptions. What are those assumptions? The applied compressive stress cannot be more than 36% of your characteristic compressive strength, and the mean temperature of the element has to be between 10 or 20 degrees centigrade, or the seasonal variations have to be between -20 to 40 degrees centigrade. That is typically in an India tropical climate, this is acceptable. And but when the temperature goes more than 40 degrees centigrade, then the coefficients have to be increased by 10%, because higher the temperature, higher will be the creep. Now, we can see we have calculated this phi naught value. Now, how to calculate this reduction factor? Again, the code gives you different empirical equations, that is again function of various parameters. You can see that is function of T naught, the age of loading, and then T, the time at which you are doing the calculation, and then beta H, which is a coefficient that depends upon the relative humidity, and the notional size coefficient. Now, again beta H is a factor that accounts for the relative humidity and the notional member size. Okay, that I think we have seen what is H naught and what is the influence of relative humidity. So, the coefficients have been derived, have been proposed based on what kind of concrete that you are dealing with. For low strength concrete, this beta H equation is valid, and for high strength concrete, this beta H equation is valid, and it also has some empirical coefficients that you can easily plug in into this equation, and you can calculate now. Now, what are these alpha 1, alpha 2, alpha 3? Now, alpha 1, alpha 2, 3 are basically the coefficients to consider the influence of concrete strength. Now, alpha 1 is 45 by FCK plus 8. Again, we sit higher the strength of the concrete, less will be the creep. So, somehow we have to account for all these effects that is coming into this equations, right. So, these are the values.